A few words about devices and drivers. In the classic Unix driver model, devices belong to one of three categories: character devices, block devices, and network devices associated driver types. Under Unix, drivers are code units linked into the kernel that run in privileged kernel mode. Generally, driver code runs on behalf of a user mode application. Access to Unix drivers from user mode application is provided via file system. In other words, devices appear to the application as a special device files that can be opened. In the beginning, all drivers were built into a monolithic kernel, and every change in a set of devices required a rebuild of the kernel. Then a mechanism for dynamically loading device drivers was developed, which made reconfiguration possible with support for dynamically changing a set of devices. Nowadays, almost all modern systems support this machinery. We just need to install a package with a new device, and this device will be supported by the system immediately. As we remember, we can access the device via pseudo file in the dev directory. And those files will be special files. We see this in the first character of the permissions field. C stands for character device and B for block device. We can work with both of them as with files, but on block device, a file system can be created. What about file size? In the place of the size, we see two strange numbers that have nothing to do with, for example, the actual size of device. To understand the meaning of those numbers, we just take a quick look at the organization of the device subsystem in a Unix-like kernel. From the very beginning, drivers in the Unix kernel were placed in two special tables: CDFSW and BDEF. SW. CDEF SW and BDEF SW. Character and block device switches. Those tables have a separate row for each device driver. And the first number of two, so-called major number, is just a position in this table. Each driver places the initial entry points for the standard file functions in its on table row. Open, close, read, write, seek, and everything that did not fit into those functions into the IOCTL input-output control function. To write a new driver, you just need to implement such functions for your device. Okay, but what about the second number, the so-called minor number? Let's take a look at the dev directory again. It's look interesting. We have the same major number for all devices, dev null, dev zero, and even dev mem. This means that they are all handled by the same driver. And one more thing. As we can see, all hard disks with all partitions are also handled by one driver. This is only one difference between those files, the minor number. And this is just a parameter that is passed to the driver. But by this minor number, the driver understands which device we need. Dev null, dev zero, or dev mem, or what hard disk or partition we are working with. And in the old days, device special files in the dev directory were created by the mknode utility in the make dev script with a fixed major and minor numbers. Today, all device files are created automatically on the special device file systems. But the mknode utility can be useful in some cases. As we can see, we can create special files by choosing the device type. C for a character and B for block devices. But we also have a very special file type, P, for so-called named pipes. We can use it as a shells, channels for inter-process communications, but with entry point into your file system hierarchy. As we can see, we send the data from one process and get the data, this data, from another process by using this named pipe. There are nothing, the data really placed on the file system or on the real file. It's just sending across the internal pipes structures as commons pipeline.